First off, these are just a few more examples of some one-sided limits that are good to kind of see and be aware of. I'm actually not going to do this first example because it's very similar to something in a previous video, but you'll actually find that on one side the limit is 1 and one side the limit is -1. So it actually proves there's a jump because you go from 1 to -1. But I do want to do this second section here, the 1 over x minus 2 squared. So 1 over x minus 2 squared. Now, they're asking us to take the limit as x approaches 2 from the right. So as I go to the table, I have to think, okay, what would be just to the right-hand side of 2? Or in other words, what would be just a little bigger than 2? So 2.1, 2.01, 2.001, and so on. Well, it looks to me like this is just getting bigger and bigger. We've got 100, 10,000, 1 million, 100 million. So the numbers are just getting larger and larger. So when that happens with a one-sided limit, we say that the limit is positive infinity. So we just put an infinity as our answer. Now let's do the same thing, but from the left-hand side. So for that we would need to do 1.9, 1.99, 1.999, and then 1.9999. You don't have to do all those if you don't want to. You can probably see the pattern is the same again. We go 100, 10,000, a million, 100 million. It's just growing larger and larger. So again, we get positive infinity. So that tells us that we actually have a vertical asymptote, and it tells us that that vertical asymptote is approaching positive infinity from both sides. So from both sides, it's going up and up towards positive infinity. So without even seeing a graph, we know that there's a vertical asymptote here simply because we took the limit as x approached 2 from both sides. Okay, now this is another one I want us to look at. Sine of 1 over x. Make sure your calculator is in radian mode. This one is. So we'll do sine of 1 over x. The 1 over x is inside the sine. Now we want to first do the limit as we approach 0 from the right-hand side. So 0.1, 0.01, 0.001, 0.0001. Now if you can tell, this one does something kind of odd. First, we're up here at -0.544 and then -0.5064. So we might think, okay, that looks like it might be heading toward -1/2, for example. But then all of a sudden it jumps up to 0.826, but then back down to -0.305. So this doesn't really appear to be heading toward any one certain value. So when it changes like this and it's not heading toward any certain value, we say it oscillates. And if it oscillates, then in that case the limit does not exist. And I'll go ahead and spoil the surprise and tell you it's going to do the exact same thing from the other side. So I want to let you get kind of a picture of what's going on here. Like I said, the word is oscillating. If you think about an oscillating fan, that means it moves back and forth, and that's exactly what oscillating means. If you were to look at a graph of this, it would do something like this. If you notice, plugging in 0 would give you a does not exist. So the function doesn't actually exist at 0. What happens is the graph goes up to 1, down to -1, up to 1, down to -1, and it does so over and over and over, and it does so more and more quickly. It does so in a shorter and shorter amount of time. In fact, if you kept zooming in on this picture, you would just keep seeing the same thing, because it forever and ever keeps bouncing back and forth as it gets closer and closer to 0. And the closer you get to 0, the faster it bounces. So this is called oscillating behavior, and it causes a limit not to exist. Now to be clear, the problem is only at 0. If we wanted to find the limit right here, that's fine, that's no problem. We're easily approaching the same thing from both sides, no weird behavior. But at 0 for this one, we've got a big problem. We can't find a limit. One thing I want to make clear though is there's a difference between what I drew originally and this picture. This one, while it is bouncing back and forth, is doing so less and less each time. So this one would have a limit at 0 because the values are getting closer and closer to a single value. Even though we're bouncing less and less each time. The problem with this first picture is it's bouncing the same amount over and over, and it does so more and more quickly. So this picture on the right hand side is kind of like dropping a bouncy ball on the floor. Yes, it bounces for a while, but eventually it's going to come to rest on the floor and it's done. The picture on the left hand side would be more like dropping a bouncy ball and then watching it bounce up to the ceiling and then come back to the floor and then bounce all the way back to the ceiling again and then back to the floor. And not only does it keep going up to the ceiling and down to the floor over and over, it keeps doing so more and more quickly. So it just always speeds up until it's going infinitely fast. So that's why there can't be a limit for that kind of a thing. So now that you have a pretty good handle on one-sided limits, we want to talk about regular limits. Now, just so you know, you're never going to actually call them regular limits. They're just limits, but I want to make sure I differentiate for you the difference between limits and one-sided limits. So regular limits consider both sides of the point, and we're going to look at how to solve them using graphical and numerical methods, and then we're going to use direct substitution to solve them analytically. So if you notice, the notation is exactly the same as it was for one-sided limits, except that there's no plus or minus in the superscript. So where there was something here before, right above the A, there's nothing there anymore because we're considering both sides. Also notice that our answer has to be a real number. It's okay with one-sided limits to have an answer of infinity or of negative infinity. We don't ever answer infinity or negative infinity with regular limits, however. So regular limits cannot have an answer or positive or negative infinity. That does not negate what we did earlier, though, with one-sided limits. One-sided limits can, regular limits cannot. Also, the regular limit exists if the function is approaching the same thing from both sides. So we saw some examples earlier where whether we approached it from the left or the right, we got the same answer. Well, in that case, we already knew the regular limit. It would just be that number, whatever number it approached from both sides. But for the problems where it approached different things on each side, that would be a time where the regular limit would not exist. So there are 3 reasons that limits don't exist, and we've actually kind of touched on all of them already, but just to lay them out for you, these are things you should have memorized. Number 1, differing behavior from the left and the right. That just means it approaches one thing from the left and something different from the right. 2 is unbounded behavior. That, again, just goes back to the infinity issue. If we approach infinity or negative infinity, then the regular limit will not exist. And finally, oscillating behavior. That's the thing I showed you with sine just a moment ago. That causes problems with both one-sided limits and regular limits. But in general, this list I'm talking about is just focused on regular limits. We just focus on them when it comes to reasons limits don't exist. Now the second list of 3 is not anything you need to memorize. It's just to try to help you understand and kind of be able to put things in categories. There are 3 different ways we'll be solving limits. Numerically, which we've already done, that's when you use a table, like in the calculator. 2 is graphically. That means you look at the graph and determine the slope, or not the slope, the limit. And 3 is analytically. That's basically algebraically. Like if you've just got pencil and paper, no calculator, no graph, how do you figure it out? So here's our first analytical method, direct substitution. And it is exactly as easy as it sounds. All you do is substitute. So in the first example, the limit as x approaches 3 of x cubed minus 4x. All you do is take the 3 and plug it in everywhere you see x. So we get 27 minus 12, and our answer is 15. Now the limit as x approaches 1. So next we do it, and we get 1 plus 2 over 1 plus 1. We get 3 halves. Okay, this bottom here we've got the square root of 4x. So square root of 4 times 4 when I plug in 4 for x. So square root of 16, which is 4. And finally, any student in my class should know this one just by looking at it, because you should know your unit circle. We plug in pi, sine of pi is 0. Now we're going to learn in the next video some more complicated analytical methods, but this one is the most straightforward, and this is the one you should always try to use. Just to give you an idea of what's coming next though, the problem comes when you have something like this. You might be asked to find the limit as x approaches 2 of x squared minus 4 over x minus 2. Now when you try direct substitution, and you should always try that first, you end up with 0 over 0. Well, that tells us that the function doesn't exist, but it doesn't necessarily mean the limit doesn't exist. So you have to use other methods to find the limit if you get 0 over 0, as we do here. So stay tuned for that.